What is symplectic geometry? This is quite hard to motivate. This is not really geometry in the standard sense, so that you can visualize many objects. So much of the motivation comes from classical mechanics. Mechanics, or is sometimes called incompressible. It's a flow, fluid motion. So I'll give you one example. Very peculiar phenomena, and this dynamics of this incompressible fluid. So you imagine, let's say here is two spheres. So the motion of incompressible, let's say incompressible. Flow on S2. This is just nothing but I presume you all know a little bit about differential manifold, right? So I can assume what your knowledge on differential manifold. And so this mathematically can be regarded as the dynamics of area preserving. Area preserving or measure preserving diffeomorphisms. And here is very famous, very classical theorems. What is this one? On spheres. So imagine the curve C is a closed embedded curve. And consider, now suppose let phi be a diffeomorphisms which preserve the measures or area. And then the following holds. Yeah. One of the following holds. Following alternatives. First, maybe Sorry. Let me erase this one. The first alternative is the following. So if C bisects the device with S2 into two equal area pieces, then you will never be able to displace C away from itself by area preserving diffeomorphisms. Then C intersect with phi C for any, this is empty set, for any area preserving diffeomorphisms. So let me write phi is diff omega S2. So this omega is area form. So let me denote. So denote by diffeomorphism of S2 is the set of area preserving diffeomorphism. And phi preserves the measure, preserved area. This area preserved. And if not, otherwise, there is some area preserving diffeomorphisms such that you can displace this curve. That's a very intuitive fact, right? So here is a very quick proof. So 2 is quite obvious. So let's first consider 2. So if C does not divide S2 into two equal area pieces, then one of the domain it has smaller area than the others. So in this case, let's say here is, and here is C. So then it's clearly you can move around. So if in this case, you can imagine just by rotation. Well, it's not really rotation, but since so one of the areas, so since is this is A1 and A2. So in this case, it's quite
simply closed curve만 생각하시는 겁니다.
Yeah. Okay, so let's consider the second case first. The first case. So if the area of this A1 is the same as the area of A2, then by the assumption, phi is area preserving. So phi of A1 also has the same area. So they must intersect. Otherwise, so if C does not intersect, then suddenly phi c should be contained in either A1 or A2. Because they do not intersect. So it must be contained one of the two disconnected components. So here, write this S2 minus C as the disconnected component. This is this. So if phi C does not intersect with C, then this must be contain one of these components. Well, then it's a contradiction. Then it's a contradiction because then it's okay. So because this curve is contained in here in this domain, here is A1, and the curve must be something like located here. So this area should be less than. So therefore, this means the area of phi of this A1 or A2, let's say A1, this should be strictly smaller than A1. But that's a contradiction. They said the area should be the same.
MT는 C와 phi C의 인터섹션이 MT예요.
Oh, yeah. So, if the curve divides the sphere into two equal area pieces, you will never, for any area preserving diffeomorphism, its images must intersect with the original curve. In fact, there are at least two intersections. Think about it. If two closed curves intersect at a unique one point, then again the similar dimorphism. So in fact, in this case, the intersection number is always greater than or equal to 2. Well, in the second case, it's hard to write down the complete proof. But you can imagine the motion of these waters. And water is so flexible. So if your curve is here, then you can somehow make first this curve into circles, small circles. Then you can easily rotate this circle to the place that does not have intersected with the original circle. So in this case, first deform this C into a circle by this area preserving transformations. It's hard, but you can imagine the motion of water. So you just stir the water so that this curve becomes circles, and then since the area must be preserved, and once we have made C becomes a circle, then you can easily by rotate, you can displace it away by a rotation. And we know rotation is certain area preserving
diffeomorphisms.
So here is some, of course this does not hold for, this kind of phenomena does not hold if you look at general diffeomorphisms. So there is something very special going on this area preserving diffeomorphisms. So in a way, the symplectic geometry is some kind of high-dimensional generalization of this particular phenomenon. So there are two ways of actually generalizing these two-dimensional pictures. There is the basic object of study here is area preserving transformation. So you can think about volume preserving or incompressible flows in general dimensions. That's one way of generalizing these two-dimensional phenomena into the high-dimensional case. And so there's more non-trivial way of generalizing this picture to the high dimensions. That's the symplectic geometry. So symplectic geometry is one of the way of generalizing, one of generalizations, high-dimensional generalization. Besides the geometry of area preserving transformation. So how do we do this? I mean, it's kind of the basic here in this geometry. The basic measurement is area. In Riemannian geometry, the basic measurements is the length of curve. But in this geometry, it's going to be the basic measurements is some kind of area of two-dimensional surface. So in this two-dimensional case, everything is two-dimensional, so it's quite easy to understand. But so this is some kind of area of surface. It's the basic measurements in this symplectic geometry. So maybe since this is the first lectures, instead of giving some detailed lectures, I would like to maybe so introduce some basic non-trivial theorems in this area, just to give you some motivation of things to come in these lectures. But still I needed to tell you something. Okay. So what is the basic tool? In differential topology, so here is some comparison. So let's try to some comparison. This with the usual differential topology. So this symplectic geometry is sort of in between the geometry and topology. So I just it's very flexible geometries in the point of geometries. On the other hand, there is very subtle rigidity going on in the point of the topological point of view. So, in the point of topologies, there are two basic objects of study in differential topologies. Yes. And I would like to divide this into two parts. One describes differential topologies, and the other part is symplectic topologies. In topology, there are two main, the basic object of study is the group of diffeomorphisms. So this is diff M. So this is the group of diffeomorphisms. So diffeomorphisms. The diffeomorphism means the smooth homeomorphisms. And then the topology usually studies how the basic object inside the manifold behaves under the action of diffeomorphism. So the basic object of study is submanifold. Some good subset inside this manifold. And the topology, the basic theme of topology is to understand the interaction between these two. The diffeomorphism acts on the submanifold and try to see what's going on. Just like in these examples, we look at this curve, and then you look at the motion of this curve under the area preserving diffeomorphism and see if they intersect or not. That's one kind of intersection theory is basically. Of submanifold is and the corresponding object of study in symplectic side is so-called the symplectic diffeomorphisms, which is, and in this two-dimensional example, is just area preserving diffeomorphisms. The diffeomorphism in this two-dimensional case, general diffeomorphism, and this two-dimensional example is area preserving diffeomorphisms, which I'll explain what this is later. So this is group of symplectic diffeomorphisms. And then, what are the submanifolds? Well, in this case, we want to look at some submanifold which reflects the property of the symplectic geometries. And it turns out there are several candidates. One of the candidates is either symplectic submanifolds, or this is some kind of the extreme opposite of the simplex submanifold is also there is a notion of Lagrangian submanifold. And in this two-dimensional example, this curve is an example of Lagrangian submanifold, but it's not symplectic. So this is an example of Lagrangian submanifold. So throughout the study, this course, this Lagrangian submanifold is one of the basic objects we are going to look at. And then we try to understand this interaction of these two objects. So Lagrange, so-called Lagrange intersection theorem. So this is sort of generalization of this geometry of these curves under the symplectic diffeomorphisms. So let's go back to this example again. There are two classes of Lagrange submarine. Two classes of curves. One is in this example S2. The small circles or small curves. And then, in a certain sense, and the large curve. So when I say large curve, see this, you cannot displace this curve by the area preserving diffeomorphisms. And the small curves will be the one which can be displaced by area preserving diffeomorphisms.
Okay, what is the symplectic diffeomorphism?
So I explain later.
All right.
That's a little bit, give you some motivation a little bit more. So, now I want to the question is, how do we, what is the main tools? Tools of studies. The main tools of study is some kind of this calculus of variations. Sometimes it's also called Morse theories. So let's start with what is right. So let's try to give some examples. What is the symplectic form? So let's say here is let me first give you that definition. I guess you all know what the differential form is, right? So let me just give you that definition. The symplectic manifold is a pair manifold is a manifold M equipped with a closed or non-degenerate closed two-fold, which denoted by omega. This omega is sometimes called symplectic form. Omega is called symplectic form. So where does this come from, by the way? So this is very hard to motivate unless we talk a little bit of this classical mechanics. So let's start with the example. Example, and then talk about a little bit of mechanics. So here is the R2n. Maybe let's start with this sphere S2 with area form. Omega is an area form. Area form is on the sphere by definition. Nowhere vanishing true form is an area form. And because we are two-dimensional surface, if we take the differential of this two form, you get three form. So it must vanish. So this closeness is automatic in this case. So this indeed a symplectic manifold. So this any compact surface with indeed any compact surface or any surface with area form in it can be regarded as a symplectic manifold. But more general, more interesting example is you look at the even-dimensional Euclidean space. So even-dimensional Euclidean space, you consider the coordinate, let's say Q1 and Qn and P1 and Pn. This coordinate, and then this coordinate. And you look at this omega 0, that written as dqj or dpz. So this is two form, and because if you take a differential, you get 0 because the d square equals 0. So this is clearly the closed two form here. So this, and it is non-degenerate. So here is what this non-degenerate means. Non-degenerate means, well, this two form is a skew symmetric. You can regard this as skew symmetric matrix. Any bilinear form can be identified with a matrix, and this two form by definition is skew symmetric bilinear form. So, and the corresponding matrix and the matrix of this bilinear form with respect to the basis dq1 dqn dp1 dpn. The standard basis, I just write differently, right? Standard basis is given by like this. This one is identity 0. Negative I, 0. So this is invariable matrix. This is n by n matrix. That is identity, n by n identity. This way. So this is identity matrix. So how do we see this? You just take the interior product, DDQ, you see it, here is the region. If you take this DDQ, the interior product, omega, and you see this becomes dpj. And dpj, the omega becomes negative dqj. So if you write this, am I doing right? So dqj goes, oh, maybe this. So what am I doing here? So this is an example. By the way, in this symplectic geometry, somehow this exterior calculus you learn in differential manifold actually plays a significant role in this geometry. So you have to be very familiar with this differential exterior calculus in doing a lot of calculation involved in symplectic geometry. So I will say a little bit more about this kind of calculus later. But at the moment, let me keep going. Okay. This is an example. So this shows you, so hence, this omega 0 is non-degenerate. Because this matrix is invariable matrix. And we know the skew symmetry matrix also has even rank. So if it is non-degenerate, this manifold must be even dimensional. So you note that. That is back. Any symplectic manifold must be of even dimension. Because the skew symmetry matrix always has even rank. Okay, so another more general example is you look at an arbitrary manifold, general arbitrary manifold. And there is no these cotangent bundles. The cotangent bundle. So this is the dual bundle of tangent bundles. Carries natural symplectic form. Omega 0, and this one has the form as negative d of theta. So this omega 0 in this case is not only exact, close, but in fact in this example it is exact. And the theta is one form, the canonical one form, which can be written as this way. Pj of dq in canonical coordinate. Maybe I explain what canonical coordinate q1, qn, p1, pn. In fact, this second example is a special case of this third example. So this second case corresponds to n to be Rn. Any question? So here is one homework. So the proof, maybe let me remind you first. Recall what the canonical coordinate. Of cotangent bundles. So now we choose a coordinate chart. Let's say phi u on this space manifold here. And phi is a mapping, right? Coordinate chart means u goes to Rn. And its coordinate function can be written as x1, xn. And when you're given this coordinate, this provides natural basis. So this one induces a canonical natural basis, or coordinate basis, or unit basis d dx1 d dxn of the tangent bundle on U. And by taking the dual basis of this one is nothing but dx1 and 1 forms. So the dual basis dx1 dxn provides a basis of the cotangent bundle restricted U. And then the canonical coordinate, this is an open subset inside this one. And the canonical coordinate on this open set V is defined in the following way. As follows. Okay, so here is the picture. Here is N. You're looking at some open set U here. And then you look at the cylinder over this. This is U. And we look at this V is nothing but this cylinder over U inside cotangent bundle. So I want to give you some coordinate on this open set V here. We already have some coordinate on this here. So we have only to describe the location of vertical fibers. So suppose you're given a point here, alpha. And how do we describe the coordinate of this point alpha? So what we do is you can look at the projections. P star n u to u. And by pulling back the coordinate here to here, we have and denote this qi to be the composition of xi in the pi. So what this function does is it describes where these fibers locate. So this here is alpha, here is pi, project here. So these n functions provides the location of their fiber. So we are only to now describe the location of this in this fiber. So how do we find out this location in the fibers? What we do is, alpha is an element in here. So let me denote. So you know that alpha is now lies in the fiber. Let me write this is Q, okay, or pi. This is a 5 element of the cotangent space of n at pi alpha. Projections. It's a one form. So, but this one provides the basis of the fiber. So, dx1 and dxn is a basis at alpha, at pi alpha provides a basis of this pi alpha of n. So therefore alpha should be, so hence alpha can be uniquely written, you can write as linear combination of this p, j equals 1 to n, of d pi alpha of xj. For a unique choice of pj. Of course, pj depends on alpha. pj alpha. So altogether, it provides a coordinate. So altogether, by combining Q1, Qn, P1, and Pn provides a basic, provides a coordinate. Coordinate on P star n and u. And this is called the canonical coordinate. This is the canonical coordinate. Associate this is the canonical coordinate. Coordinate of cotangent bundles associated to the coordinate x1 on the base. So that expression, theta, I just recall you that I'm pretty sure that most of you know what these canonical coordinates are. I just remind you, because it plays a very important role here. So here is the homework. Yes. Proof. So consider this one form written Pj of dqj, okay, written in coordinate, in canonical coordinate, are globally defined. So in other words, this coordinate zeta, and proof the zeta is globally defined. One form on cotangent bundles. So this first, actually, in fact, I'll give you the what that one form must be. Okay? And this theta is defined as follows. Yes. Okay, so when you first encounter this these forms on cotangent bundles, it's very confusing because we are looking at the tangent bundle of cotangent bundles. And so I want to make sure what you understand what's going on here. Okay? So theta is a one form on cotangent bundle. So how does this one form can be defined? How is this one form defined? So let me describe in this way. So here is n. Here is cotangent bundles. So here is a point alpha. Okay. So by definition, one form should be a linear functional on the tangent space at here. Right? So we have to provide the value against any tangent vector psi at alpha. Okay. So to define this one form, we have to evaluate theta at alpha against any tangent vector psi. Okay. So what is that value? There is only one way of producing real numbers out of this data. One is, so here is this psi is a tangent vector. Okay. So psi is a tangent vector at alpha of these cotangent bundles, as I draw here. But there is a natural projection to n. So this is pi over pi. And when you're given a map between two smooth manifolds, you can take the derivative. So if you take the derivative, then this derivative maps the tangent bundle of first manifold to the tangent bundle of second manifold. Okay. So you can project this tangent vector to the base here. So here is pi alpha. And if you project by d pi, you get some vector here. So this is d pi psi. So So this one is a tangent vector of n at pi alpha. And on the other hand, original alpha is a covector at pi alpha. So therefore you compare this alpha against this tangent vector. So this definition is nothing but that pairing. So natural pairing, alpha evaluated that tangent vector. So as you can see, it gives a unique definition. There's canonical invariant definition. It does not depend on the coordinate. And what I want to prove is this one form is indeed can be written in this expression in canonical coordinate. That's what we are going to prove. So to prove this statement, just to prove this L alpha can be written in this way in canonical coordinate. Then you are done. So in this so therefore in canonical coordinate, this omega negative d theta is written, omega 0 can be written as n j equal 1 dqj of dpj. So this is precisely the symplectic form I gave you on even dimensional Euclidean space. In fact, the basic theorems in symplectic geometries is so-called double theorems. Says, for any symplectic manifold you are given, that for any point x in M, there is some coordinate, there exists a coordinate q1, qn, p1, pn, such that this symplectic form can be written as this. So any symplectic form can be written into the canonical symplectic form on Euclidean space. So this double theorem tells you that there is no local invariant of symplectic manifold, because every symplectic manifold is locally the same. So what this says, so here the consequence, so every respect double theorem, the corollary, double theorem says there is no, there is all symplectic manifolds are locally isomorphic, locally the same, as long as dimensions, if their dimensions are the same. In fact, any symplectic manifold local isomorphic, so in fact, any symplectic manifold M omega is isomorphic, locally isomorphic. To the standard Euclidean space, even dimensional Euclidean space. Any question? So it looks like the symplectic topology, symplectic geometry is very much like differential topology. In differential topology, we know that any manifold is locally Euclidean. So the only local invariant in differential topology is just dimension. So exactly the same thing has happened in the symplectic geometries. The only invariant, local invariant, is dimension. So in old days, people sort of have a very hard time to find some kind of invariant of symplectic manifold because there is no way to construct local invariant, unlike in Riemannian geometry. In Riemannian geometries, there are plenty of local invariants, like curvatures. Right? If you are given Riemannian metric, we know that this curvature is a local invariant. But there is no notion of this curvature in symplectic geometry. So if there is any invariant in symplectic manifold, it must be very global. So one of the consequences of the double theorem is the following. It is corollary. So there exists a symplectic invariant. Let me denote by B2n delta is the ball of radius delta in Euclidean space. Then there is and that M omega is a symplectic manifold is given, and that X is in M given. And then, here is the Euclidean space. Here is the ball of radius, solid ball of radius delta. And here is there's a manifold M, symplectic manifold M. I choose X. Yeah? And the question is, can you find some embedding of that ball in this M by some symplectic embedding? So the question is, let me symplectic embedding. So maybe I have to introduce the definitions before talking about this. So let me first define a symplectic map. So map phi between two manifolds, two symplectic manifolds, omega 1 to M2 omega 2 is called symplectic. If this map pulls back, you can pull back differential forms and compare this form with omega 1. If they coincide, then we say this map is called symplectic. So the question is, suppose you're given standard ball inside Euclidean space. And then the double theorem basically, what double theorem is saying is that there is some symplectic embedding. So double theorems says that then there is a symplectic embedding phi of the standard ball B2 and delta with the standard symplectic form into the given symplectic manifold with its center is mapped to X for some delta, if delta is sufficiently small. That embedding is nothing but the inverse of the coordinate chart. Will provide such an embedding. The coordinate chart maps from here to there. And the double theorem basically said there is some coordinate chart such that in that canonical coordinate, this form, omega, can be written in the standard form. So if you choose sufficiently small ball, that will be the image of the standard ball. So you can interpret that coordinate chart as the symplectic embedding of standard ball into M. Okay. So we know there exists, if you choose sufficiently small delta, then you can always find the symplectic embedding. The natural question is, how big can you choose this ball? The question is, how big delta can we choose? So it turns out this maximal possible delta is very important invariant. So we can define this sometimes Gromov capacity. Let me denote this C of M omega is the supremum of delta such that supremum over, let's say, delta such that there exists a symplectic embedding phi from B2 and delta omega 0 into M omega. And the double theorem basically says this number is always positive. So double theorem basically implies this M omega is always positive if M is compact. Now the question is whether this kind of invariant is really something non-trivial. So to test whether this is a good invariant or not, let's look at very simple examples. This is the question is asked by Arnold and Gromov. Questions. This is asked around 1960s. The question is the following. Suppose you look at G2n or G2n of R. This is radius r times the Cn minus 1. So Cn minus 1, you regard this as R2n minus 2. Okay? We are going to, the complex coordinate Gj is going to be Qj plus I times Pj. In this way, you can identify Cn with it. So this is the cylinder over disk. So here is disk. This is R. And this direction is C, one of the C factor, and this direction is C to the n minus 1. Okay. The point is this disk only C. So this disk involves both Q and P coordinate. And they asked what are the maximum value. So the question is the following. The question is whether that Gromov capacity, by now it's called Gromov capacity, is greater than R. Okay, that's the question. So the question can be asked in the following way. Suppose you're given this ball of radius capital R. Okay. And the question is, does there exist some symplectic embedding phi? Another way of saying this is whether that Gromov capacity is greater than this small r. But this is very, when this has finite volume, if you imagine the motion of incompressible flow, the water motion, you can certainly squeeze this big ball and put it in here by area, let's say, measure preserving diffeomorphism. The question is whether can you do this by symplectic diffeomorphisms. So if R is smaller than R, then there is obvious embedding, just a rigid embedding. Can we put this into here? The non-trivial question is, can you find an embedding when R, the capital R is greater than little r? So here is Gromov's non-squeezing theorems. And there is no, if this R is greater than R, then there is no such symplectic embedding. Symplectic embedding of E to R into Z to R. This is a very amazing result if you try to compare the symplectic diffeomorphism with this measure preserving diffeomorphisms. As I said, there is, if you look at the incompressible flows, then you can squeeze without changing the volume and into here. But you cannot do this by symplectic diffeomorphism. Symplectic embedding. So there is something going on these symplectic properties. And another important point here. So the corollary of this non-squeezing theorem is the Gromov capacity of this G2 and R omega 0 is exactly R. Actually, usually we look at the pi delta square, the area. So this is pi r squared. That's what this Gromov non-squeezing theorem. This is the beginning of this whole area of symplectic topologies. This has many consequences. So I want to say about those things. But before finishing today's lecture, I want to make one remark. It is crucial, in these theorems, it is crucial that this disk D2R is a disk in C. C is Q1 and P1. So this coordinate plane involves this Q and P coordinate. So this is, but if you choose this disk, if D2R, let's say D2 is contained in, let's say R2. Let's say the Q1 and Q2 coordinate R2, Q1 and Q2, not Q1 and P1, cross the rest. Then there is such a squeezing. You can easily squeeze. In this case, we can squeeze this B, we can find on the B train R into this D2 cross, let's say D2 Q1 and Q2, that's the rest of, let's say Q3 and Qn, P1 and Pn. Okay, because you can just imagine phi Q1 and Qn, P1 and Pn. Let's just define like this. Okay? You multiply, right? We want to make this Q1, Q2 size of Q1, Q2 direction very small. So you can just multiply small number, delta Q1, delta Q2, and the rest of the coordinate the same here. But you want to make symplectic maps. So what you have to do is you divide by delta 1, P1, delta P2, and the rest are the same. You can check this is indeed a symplectic mapping, because the symplectic form, you recall, symplectic form was written as dqj of dpj. So if you multiply here delta in this coordinate and divide by delta for the corresponding conjugate coordinate, then this form doesn't change. So what this means, you can squeeze in this Q1 and Q2 direction while you dilate the P1 and P2 direction. That way you can squeeze. But you cannot do that kind of operation if you choose this disk in that Q1 and P1, this disk in the conjugate coordinate. So this is very subtle rigidities. And the proof is, this proof really is highly non-trivial. And in fact, Gromov introduced this whole technology of so-called pseudo-holomorphic curves into the symplectic geometries, and this can be proved only after he introduced these analytical machineries. 오늘은 그만하겠습니다. 질문 있습니다.